model identification. This is important. It's kind of a little funny, but at least when I first was learning this, seemed counterintuitive to me. This is very important, especially if you get into structural equation modeling. You can have models that are either under-identified, over-identified, or just identified. It's just like, it's kind of the three bears, but it's different because which is the best bet, may not work with that analogy. In an under-identified model, that means there's not enough information to estimate a model. So you may try to, in structural equation modeling, you may try to plug in some design, and it'll kick back and say the model is under-identified. That's the way of telling you there's not enough information here for me to solve it. You can think of it, and remember, how did we solve those? When we solved the coefficients by hand, those paths, we had those 3, A, B, and C, and we needed 3 correlations to be able to go back and solve them. What if I only gave you 2 correlations? You can't solve it. So an under-identified model is kind of like saying x plus y equals 5. What's x? Not necessarily. What could x be? 3, 2, 7, anything. -50. It could be anything. There's not enough information. You can't solve that problem. It just comes down to whatever pops in your head. You can have a just identified model where there's just enough information. That's what we did earlier. We had 3 variables we needed to solve, and we had 3 unknowns we needed to solve, A, B, and C, and we had 3 correlations to do it. We were just right to solve. So that's saying x plus y equals 5 and x minus y equals 1. Now what's x? 3. And x has to be 3. It can't be anything else or it's not going to work. And you can have what's called an over-identified model. This is where there's more information than is needed to solve the model. Now, that may also seem kind of crazy. That may seem a little crazy. That's like, so you can think that x plus y is 5, x minus y is 1, and x times y is 4. What's x? There's no solution, no definitive solution. What you end up with an over-identified model is solving to as good of an estimate of x as possible given those constraints. But you're not able to, we know x has to be 3 for these 2, and we know x isn't, if based on these 2, x and y are 3 and 2, but we know x and y can't be 3 and 2 to solve that. So you end up in a situation you can't definitively solve it. And instead, the computer will go through and find values of x and y to come up with values that are as close as possible to solving those equations. Now you might think, well, that's kind of stupid. Why would you ever want to do an over-identified model when you can do a just-identified model and come up with a perfect solution? But what's nice about over-identified models is it allows you to evaluate the quality of a model. Because you can have a model where when it's trying to solve what are the best values that are just completely crazy from reality. Now I'm kind of giving you a little segue into structural equation modeling. One of the beautiful things you can do with structural equation modeling is you design a model, and here's where I may have a model, and Ming may have a model, and Anika may have a model, and we can then plug in the data. We collect data, we plug in the data, we have an over-identified model. And it comes back and says, well, based on if all of our models are over-identified, it can come back and say, well, based on Anika's model, I'm able to come up with values that are very close to what your data suggest. You know, I'm going through and estimating, I plug in the raw data you've got, here's the values, and it looks really good. It's not perfect, but it looks really good. Ming's, okay, I plug in for Ming's model, and I'm able to, based on his model represents reality. So let me think of another, let me take a step back. In a way, what it's saying is Anika's model reflects reality pretty darn well. It's pretty close to what you're really seeing in the data. Ming's model may, with the exact same data, come back and it's okay, it doesn't quite reflect reality, it doesn't quite reflect the data as well as Anika's. But it's pretty good. And then it looks at my model, and the values that's coming back are completely crazy. And it says that model's completely nuts. It doesn't reflect reality at all. You're able to start to compare one model versus another model versus another model with reality of the data and pit mano a mano, one model versus another model, and may the best, whose cuisine reigns supreme? No Iron Chef. I got to slip an Iron Chef thing in here. Iron Chef? Iron Chef? Whose cuisine? Oh, Google Iron Chef. The Japanese version, not the American one. Anyway, you're able to pit one model against another model to see which model ends up looking better with reality. To do that, you need over-identified models. So we tend to, in structural equation modeling, we like over-identified models because it allows you to estimate the quality of a model. In a just identified model, it will give you a perfect solution, but no way of actually evaluating whether that reflects reality, how well that reflects reality, because it's just the math. Multiple regression, doing path analysis in multiple regression requires actually a just identified model. When we do multiple regression, path analysis in multiple regression, we're basing it on just identified models.
So which model you have depends on the number of variables in the model, or how do you know when you have a over-identified?
We'll get to that in just a minute. Kind of how do you end up with an over-identified model or an under-identified model? We'll get to that later. It's related to, think about what were we trying to do before? We have three correlations. We have three pieces of information, and we had to estimate exactly three paths. That's why it was just identified. An over-identified model, I may have three pieces of information, but I'm only estimating two paths. And that's where you run into trouble, that this one of those pieces of information may really not fit with what you're expecting with these. Because like here, I've got three pieces of, I've only got two, did I say that right? Two pieces of information, anyway. More information available than needed. So I've got, I need to go back and check my tape. We'll actually take a break in just a minute so I know where to clip this. So for a just identified model, let me start again so I can cut it cleanly. For a just identified model, we had three pieces of information and we were estimating three paths. For an over-identified model, more information is available than is needed. So that would be, I've got three correlations, but we're only estimating two paths. And so those three correlations, you can end up with a situation where you can't make it all work perfectly. An under-identified model is there's not enough information to estimate the model. I've got three paths, but only two correlations. I'm completely stuck in the end. So you can, from your models, you can start to think about, well, what happens then if I have we have the same variables, but you have some paths that I don't have, and more paths and fewer paths and stuff. Changing the paths is how you can go from under, over, or just identified. Regression, though, when you do this in multiple regression, it's very constrained. The model, you don't have the flexibility in how you design the model. You have a specific sequential order, and that order completely defines what your model looks like, as we'll see in a minute. Structural equation modeling gives you more flexibility. Some other technical jargon: exogenous variables. That's any variable, any influence that's outside of the model. Oh, I'm sorry. For exogenous variables, any influence on an exogenous variable is outside of the model. So they're like that first variable in the chain, in that sequence. Anything influencing an exogenous variable, there might be things influencing mom's education, but my data has no arrows pointing to mom's education. Anything influencing mom's education is not in my data set. It's not in the model. Versus endogenous variables are influenced by other variables in the model. Mom's education influenced our studying, so our studying is endogenous. And then unmeasured variables we talked about. Those are circles or ellipses, and they're actually not a variable in our data. We're not actually measuring them. Now, common causes, then we'll take a break. Common causes in experimental designs. You don't have this slide. I just added this today. Wanted to talk about this a little bit. Something just to keep in mind, that just like with multiple regression, you have to have all common causes in a path model, because we're doing this with multiple regression, so it makes sense that those same rules apply. And you have to a key point to remember when we talk about making sure you include common causes. Well, there's 2 points I want to talk about. One is that common causes are not just predictors of the outcome, or factors that are influencing whatever your variable of interest is. Common causes influence both the outcome and the variable of interest. If something's only influencing one or the other, it's not a common cause. Right? So people will often misinterpret that. Keith talks about that. People will often misinterpret that and think, well, I have to have everything that influences the outcome and or everything that influences my predictor. No, common causes are something that influences both the outcome and your predictor of interest. This leads to, you can kind of see why we need it in this model here. I've got, I'm looking at an intervention, predicting grades, and I want to look at the effect of my intervention in this path model. And for this intervention, notice I'm saying teacher choice. Teachers are picking which kids get the intervention. It might be the teacher just says, this kid needs it, this kid doesn't, or it might be the teacher decides, I'm going to do the intervention, and I don't want to do that stuff. So teachers just it's up to the teacher to decide whether they're going to do the intervention. I need to, because there's factors that may influence whether the teacher does the intervention, I need to include any common cause that may influence why a teacher decides to do an intervention, as well as if I need to include any factor that influences whether the teacher does the intervention, if that also influences a student's grades. So for example, if the teacher's gender has no influence on teachers' grades, I don't need it in my model, because it's not a common cause for both. But in a situation like this, you can see how hard it might be to come up with the common causes. What are factors that may influence a teacher deciding or a teacher offering an intervention that also influence a child's grades? Well, it might be a motivated teacher, kind of a gung-ho or energetic teacher, or a burned out teacher. If I'm a completely burned out teacher, I'm not going to want to start a new intervention. So I'm going to say no. And if I'm a really burned out teacher, maybe my kids' grades aren't as good either. It might be the parents. I am a motivated, educated, involved parent, and I make sure my kid gets in classes with those really cool teachers that do things like this. Because I'll just, if you haven't been one of those parents, you probably know some of those parents that'll do that. And that also leads to, that same engaged, involved, motivated parent also leads to higher grades. So that's another common cause you need to include. There's lots of things that could be influencing both of those. And technically, anything that influences both needs to be in the model, because we're back to who gets the C, who gets that overlap. Motivated parent gets the overlap. Engaged, burnt out teacher, not burnt out teacher gets the overlap. And so you've got to take those effects out as part of the causal model. But that can be really hard. I mean, there's so many things that could influence that. This is why we love random assignment, and why you will see people like me begging and pleading and whining and cajoling teachers and principals and superintendents and faculty do a random assignment. Because, think about it. Here's if the beauty of random or a kind of that true experimental design with randomization is the randomization removes the effect of all the factors related to whether or not a child gets the intervention. Suddenly, that path disappears. Because by randomizing motivated, who gets the intervention? Motivated parent teachers, unmotivated teachers. Engaged parents, unengaged parents. It's all random. That magic of the random assignment removes the effect that all those possible factors have on who gets the intervention. Suddenly, you don't give a crap about common causes anymore. They're not your problem. You've magically eliminated that incredible burden and problem of controlling for all the common causes just by the beauty of randomization. They may still be related to grades, but because they're uncorrelated, when you have variables, when you have an effect and you have other variables that are uncorrelated, remember, they have no impact on that regression coefficient. That standardized beta, you can add in motivation, parents, teachers, kids, whatever, and they may all be significant, and it will have no impact at all on what that regression effect is. That's why we like, visually you can see from a path model. I think it's just kind of a really cool way of seeing why we like randomization. From the common cause perspective, it removes that path, and by removing that path, there are no common causes to worry about. This is why education should do randomized studies, and we are probably one of the worst behavioral disciplines for doing it. Because people will argue it's not good for the kids, and I will passionately argue that is baloney. Giving a bad intervention is not good for the kids. Wasting their time is not good for the kids. This is how you find out, are things good? But on that note, I will get off my soapbox and we will take a break. Thanks.